know Earth's early atmosphere did not have oxygen in it? Well, there's a bunch of different lines of evidence that show us this. One of the things is detrital pyrite and uraninite. Okay, first of all, detrital refers to when you have broken bits and pieces of sediment that go into making a new sedimentary rock. That's detrital. Now, why would we care about detrital pyrite and uraninite? Both of these easily degrade in an oxygen-rich atmosphere. Yet we have like a pyrite conglomerate here. Notice these little pyrite pieces are nicely rounded. That means these pieces of pyrite rolled around in a stream or on a beach and got nicely rounded over time. Well, that couldn't happen if we had a lot of oxygen, because the oxygen would decay the mineral and it wouldn't be able to even survive long enough to get rounded. And so we can find this detrital pyrite and uraninite, and that lets us know this oxygen that really breaks down those minerals quickly didn't exist at that time. There's also no red beds. Now remember, when we talked about what color in sedimentary rock means, red tells us that we have iron oxide in them, and hematite is the mineral. And well, we can't oxide something if we don't have oxygen, right? So we have no red beds because there is no oxygen to create them. No carbonate rocks at this time. Carbonate is calcium carbonate, carbon and oxygen bonded together. We don't have any of these carbonate rocks. And then by far one of the biggest things is we have these things called banded iron formations, which we call BIFs. And certain iron oxides can only form if oxygen is present. And these banded iron formations are made from those iron oxides. And most of these banded iron formations date to 2.5 to 1.8 billion years ago, that great oxidation event. So basically what was happening when there's no oxygen, no O2 in the atmosphere, iron can easily dissolve in water. But when oxygen is present, the iron likes to bond with it, it combines with it, but when it combines with it to create an iron oxide, it becomes insoluble. So during this great oxidation event where we have all this oxygen being added, the iron in the global oceans was bonding to that oxygen, sinking to the bottom, and creating those banded iron formations. So those really tell us that they kind of hold the key to showing us that we went from a no oxygen atmosphere to an atmosphere with oxygen in it. All right, another very important thing from the Hadean and Archaean that happens is we start getting plate tectonics. You must remember from physical geology, like how important plate tectonics was. It explained all kinds of different things. Well, let's see about how plate tectonics operated in the past, in the distant past. So early on, we only had this mafic ocean crust that formed by about 4.5 billion years ago. So just imagine this nice basaltic ocean crust. We have, as I already said, felsic continental crust from partial melting, starting from those zircons. We know it existed. And some of our oldest preserved, so we're not just talking minerals, but actual chunks of preserved continental crust are the Acosta gneiss and the Amazon gneiss, which are 3.8 or 4.04 billion years ago. Now, if we looked at Earth, early Earth, let's say we had a space station and could look down on Earth in the Archaean, what we would see would be this. We'd have these tiny little bits of early continental crust, tiny little areas, and they'd be floating around in this green ocean. And the ocean's green because our atmosphere is different and there's a whole buttload of dissolved iron in those oceans, which actually changed the color of the oceans. So it'd be looking down on this like weird little green planet with tiny little bits of continent, which is very different from today, where we now have the blue oceans and larger continents that have developed. And so what happened, so early on, our continents were tiny. They were very small. By about 3.46 billion years ago, they were above sea level. They had been built upwards enough that they're now sticking out of the oceans. And these continents grew over time. And how do they grow? They grow through the collisions of other continental blocks. So you basically would have a continent, and then remember subduction, right? You have one plate sinking under another. It might be bringing another continental chunk, another terrain to it, which collides with the initial one, and our continent grows over time. For the first few million years of Earth history, plate tectonics was not active, as best as we know it, and then it eventually kicked off. Now, if you want to be like, do some amazing research in geology, we are still working on understanding exactly when and how early plate tectonics began and operated. So this is something where a lot of research is still being done today. Now, early plate tectonics was probably a lot faster and a lot more vigorous. And that's because the energy behind it, the heat inside the Earth, well, it was a lot hotter. So we probably had quite a bit faster and crazier plate tectonics at that time. All right, so let's look in more detail at this accretion of the continents, this growth of the continents over time. And this comes down to, if we look at the ancient Archaean cores of continents, we have what are called greenstone belts and granite gneiss complexes. So what are these greenstone belts? Metavolcanics and metasediments, okay? Well, if you stick meta in front of a word, it means metamorphosed. So we're looking at metamorphosed volcanics and metamorphosed sediments. In particular, these are going to be komatiites, pillow-basalts, greywacke, and breccia. So we're looking at basically kind of oceanic crust and some of the sediments that accumulates on top of oceanic crusts. And so these are thought to represent pieces of ocean crust and then some early island arcs. Remember, an island arc is something sort of like Japan today, or the Aleutian Islands today, where we have these larger volcanoes developing due to a subduction zone. And right here, as part of a greenstone belt, notice those nice pillow basalts right there. And these pillow basalts are 2.7 billion years old. So we are looking at Archaean pillow basalts. And these are some of the breccias that I was talking about. This is also 2.7 billion years old, and this was an underwater debris flow, basically a lahar washing off an underwater lahar coming off one of those island arcs. So that's kind of what you'd expect in a greenstone belt. Now, what about these granite gneiss complexes? Well, remember, granite is what continental crust is made out of. Gneiss can be metamorphosed granite. And so what we're looking at here is heated and deformed felsic material that represents these early chunks of continental crust. And that might be something like this beautiful gneiss that we see here. And let's see, that is 3.5 billion year old gneiss. And so again, our nice Archaean gneiss. All right, but let's put all of this together. If we were to make a map of some of the ancient Archaean areas. And this, just to get you oriented, this is the Upper Peninsula of Michigan, that's Lake Superior, here's Hudson Bay, so we're kind of looking at parts of Canada here. And if you notice, you have these volcanic, right, your greenstone belts basically, and then you're going to have some of your granite gneiss complex. Greenstone belt, granite gneiss complex. See how they kind of alternate each other? The reason this happened is the way that our continent grew over time. We would have our early continental crust, and then we'd get a island arc smashed up against that, and then in that subduction we'd also get bits of the ocean crust scraped up, and then we get another one added, and so you end up with these kind of greenstone belts, then the continental crust, and then greenstone belts, and then continental crust, sort of alternating each other as these areas built. Now, just as a review, when we talk about stuff, over time our continent ended up growing, and ultimately we get this craton, right? The last area we looked at was right here in the Canadian Shield. But basically we get this craton, this stable area. The shield, like what we were just looking at, is where those oldest of rocks are exposed for us. The platform is where things are covered, old rocks are covered by younger sediment, and then the basement is the basic foundation of the continent. All right, so in North America, the shield is called the Canadian Shield because most of it is exposed in Canada, although there are some places you can see it in the United States. And this is going to consist of those Archean provinces sutured together. So that's that granite gneiss complex, greenstone, granite gneiss, greenstone, where they all got smushed together on that subduction zone and slowly grew this early continent. And let's look at how the continent came together. So here we have, over 2 billion years ago, we have some of our Archean cratons, right? Our original chunks of these Archean crust. And there we have a collision where, notice, this block gets added here, right? With our arc rocks, which would be our greenstone rocks, stuck between it. And as we go through time, we're going to have more collisions adding material together. Now notice this and this block come together in another orogeny, another mountain building event. Now we slammed this one in there. And so hopefully, as you can see, over time, more and more provinces, more and more crust ends up getting added to North America, making those basement rocks, the foundation of the continent, grow over time until we ultimately get the continent we know of today. And so I have a couple of maps. They all show the same thing, depends which one you like. Again, here's our Archean original continent, and there's some of the younger areas added. This shows the same thing, the old Archean here with younger added around the edges. They all show you that. But just remember, the original area is those granite gneiss complexes and greenstone flows up here, and then through more and more subduction and orogeny, more of those basement rocks that make the foundation of North America were added over time during the Archean and ultimately Proterozoic. And this is our random picture of the day. That is me enjoying a greenstone belt.